Hello class, this is Fire Service Hydraulics and Water Supply, Chapter 12, Principles of Fire Service. We will be covering several objectives and we'll start with Learning Objective 1. Learning Objective 1 states the historical method of friction loss calculations. Method 2 demonstrates how to calculate friction loss using the modern friction loss formula. Objective 3 demonstrates how to determine elevation pressure between a fire pump and a nozzle. And 4 demonstrates how various types of hose layouts affect total pressure loss. Objective 5 states the different methods for determining fireground hydraulic calculations. Let's talk about pressure loss. One of the most basic requirements of a driver operator is to deliver the apparatus safely to an emergency scene, deliver water at adequate pressure and volume to the hose lines and master stream appliances, and this is accomplished by making sure that the water supply has been established and the fire pump is set to discharge water at an appropriate pressure for a hose lay or a master stream device. Pressure loss means necessary pump pressure equals pump discharge pressure. To determine the required pump discharge pressure, you must first determine all potential pressure losses in the hose system. To deliver required pump discharge pressure, these pressure losses must be overcome. Sources of pressure loss include friction between the water, the inner surface of the hose and piping through which it is traveling, and pressure losses as water travels through hose appliances. Pressure lost or gained because of the difference in elevation between pump and discharge point also plays a factor. None of the formulas or methods used to determine friction loss is guaranteed or expected to determine exact pressure loss. Actual figures will vary for many reasons. In most cases, calculations in this chapter will result in somewhat higher water supply figures than those found in actual use. Operating at calculated pressures will likely supply a little more water than is needed rather than a little less. For pressure loss calculations, calculations assume that plain water is flowing through hoses and appliances. Any additive introduced into the water will make it slipperier and reduce friction loss. No mathematical methods have been developed for calculating pressure loss or required pump discharge pressures when water additives are in use. The best recommendation is to reduce the final answer by about 25% or so. The historical method of friction loss. The underwriter's formulas. Among the earliest available for computing pressure loss, pump discharge of pressure is not available to use now. It's not advisable to use now. Formulas were based off of old hose technology that had rougher hose linings. Calculating pressure loss will produce figures significantly higher in friction loss than actually occurs in modern hose. Different formulas were required based on amount of water being flowed. Newer formulas discussed are good for any flow. To produce effective fire streams, you must know the amount of friction loss in the fire hose between the pumper and the nozzle. Friction loss is caused by a number of factors: hose and coupling condition, kinks, bends, and primary determinant is the volume of water flowing per minute, taking into account the length and diameter of the hose line. Underwriter's formula was based on a number of premises that now limit its usefulness. When the formula was developed, the fire service basically used 3/4 inch or 1 inch non-collapsible booster line and 2.5-inch double-jacketed rubber-lined fire hose. Pump operators rarely needed to calculate friction loss in booster hose because a set amount was stated on the reel. Friction loss formula was developed based on tests conducted on 2.5-inch hose. Other sizes of hose would require additional calculations. Historical method of friction loss calculations. Since the amount of hose used between the pumper and nozzle would not always be the same, consider friction loss in pounds per square inch or PSI per 100 feet of hose. If more than 100 feet of 2.5-inch hose were used, the driver operator would have to multiply the final answers derived using the formula by the number of hundreds of feet of hose in use. Because of technology limitations, it was impossible to arrive at a single formula that would be accurate for all flows of water through 2.5-inch hose. If you look at equation 12.1 in your book, base friction loss formula using old calculation methods was the formula for determining friction loss in 100 feet of 2.5-inch double-jacketed rubber-lined hose when flowing 100 gallons or more. Now we use the formula friction loss equals 2Q squared plus Q, given that friction loss, or FL, is friction loss per 100 feet of 2.5-inch hose, and Q is hundreds of gallons a minute flowing, which is total flow divided by 100. If you look at equation 12.1 in your book on page 280, you see the U.S. customary old flow formula, which is FL equals 2Q squared plus Q, given that FL equals friction loss per 100 feet of 2.5-inch hose, and Q equals hundreds of gallons a minute flowing, which is total flow divided by 100. Using equation 12.1, calculate the friction loss in 100 feet of 2.5-inch hose flowing 300 gallons a minute through a fog nozzle. So you use the formula FL equals 2Q squared plus Q. FL equals 2 times 300 divided by 100 squared plus 300 divided by 100. The friction loss is, once you work out the math, 2 times 3 squared plus 3. The friction loss is 2.9 plus 3. And the friction loss equals 18 plus 3. So friction loss equals 21 psi per 100 square feet. Your friction loss equals 2Q squared plus Q. So your friction loss, once you work out the math, is 2 times 328 divided by 100 squared plus 328 divided by 100. So the friction loss, once you work out the math, is 2 times 3.28 squared plus 3.28. And the friction loss is 2 times 10.76 plus 3.28. So the friction loss is 24.8 or 25 psi per square feet. A portable master screen device equipped with a 250 gallon per minute fog nozzle is being supplied by a 50 single foot section of 2.5-inch hose. Calculate the friction loss in this section of hose using equation 12.1. So you've got friction loss equals 2 times Q squared plus Q. So the friction loss, once you plug in the numbers, is 2 times 2.5 squared plus 2.5. So the friction loss, once you work out the math, is 2 times 6.25 plus 2.5. So the friction loss is 12.5 plus 2.5, and the friction loss ultimately works out to 1500 psi per 100 feet. The friction loss for 50 feet equals the total length in feet divided by 100, and the friction loss per 100 feet. The friction loss for 50 feet equals 0.5 times 15 psi. So the friction loss for 50 feet is 7.5 psi. For example 12.1, using equation 12.1, calculate the friction loss in a 2.5 inch attack line that is 250 feet long and is equipped with a 1 1/8 inch tip discharging at 50 psi. So you have to use your flow rate equals 29.7, which is your coefficient, times diameter squared times the square root of the nozzle pressure. And when you work out the math, you plug in the numbers. You get 29.7, which is your coefficient, 1.125 squared, which is your nozzle, plus the square root of 50. The Q equals 29.7 times 1.2656 times 707. That gives you a flow rate of 266 gallons per minute flowing. To work out the friction loss, you have friction loss equals 2Q squared plus 2. So if you plug in the numbers, you have friction loss equals 2 times, that's your coefficient, times 2.66 squared plus 2.66. So friction loss equals 2 times 7.08 plus 2.66. The friction loss equals 14.16 plus 2.66. And the friction loss ultimately comes out to be 16.8 or 17 psi per 100 square feet. So the friction loss for 250 feet is the total length in feet divided by 100 and friction loss per 100 feet. So the friction loss for 250 feet is 2.5 times 17 psi, and the friction loss for 250 feet is 42.5 psi. The underwriter's formula was not particularly accurate for water flows less than 100 gallons per minute. Friction loss for flows less than 100 gallons per minute in 2.5 inch hose was consistently somewhat less than calculated using equation 12.1. Low flows were more laminar in form than turbulent. Laminar flows have less friction than turbulent flows. When calculating friction loss for a single 2.5 inch hose of flows than less than 100 gallons per minute, remember the original formula could be adjusted slightly to produce a more accurate result for small flows. So here's equation 12.2 for US customary. Friction loss equals 2Q squared plus 1/2 Q, given that FL stands for friction loss per 100 feet of 2.5 inch hose, and Q stands for hundreds of gallons per minute flowing. That's your total flow divided by 100. So using equation 12.2, we can calculate the friction loss in a 2.5 inch hose that is 400 feet long and flowing 90 gallons per minute. So here's our formula. FL, which is friction loss, equals 2Q squared plus 1/2 Q. So let's plug in the numbers. Friction loss equals 2 times 0.9 squared, 0.9 is our coefficient, plus 0.5 times 0.9. So friction loss equals 2 times 0.81 plus 0.45. And when you work out the math, you end up with friction loss equals 1.62 plus 0.45. So the friction loss is 2.07 or 2 psi per 100 feet of 2.5 inch hose. And down at the bottom, you see friction loss for 400 feet equals 4 times 2 psi. So the friction loss for 400 feet of hose is 8 psi. This is the table for calculating friction loss for hose other than 2.5 inch hose. and eventually you'll get this memorized. But this chart is very important because it helps you figure out the coefficient for different size hoses and what you divide by and multiply by to get an accurate reading. This is the remainder of the table for the conversion factors for finding friction loss. When calculating friction loss for a hose other than 2.5-inch hose, let's use the U.S. customary example 12.6 from your book. Determine the friction loss per 100 feet of 1.5-inch hose flowing at 95 gallons per minute. Because the flow is less than 100 gallons per minute, we will use equation 12.2. This equation reads, friction loss equals 2Q squared plus 1/2 times 1/2 Q. So the friction loss, once you plug in the numbers, is 2 times 0.95 squared, that's your coefficient, plus 0.5 plus 0.95, because that's your flow rate. Your flow rate then, or friction loss, then equals 2 times 0.9025 plus 0.475. And when you finish extrapolating the math, you get friction loss equals 0.72 plus 0.30, and your friction loss ultimately works out to 2.28 or 2 psi per 100 feet of 2.5-inch hose. To convert this figure to friction loss in 1.5-inch hose, locate the appropriate conversion factors in table 12.1. For 1.5-inch hose, we have the option of multiplying the above figure by 13.5 or dividing it by 0.074, which is the reciprocal of 13.5. So we have friction loss of 1.5-inch equals 2 times 13.5 equals 27 psi per 100 feet of 1.5-inch hose, or friction loss of 1.5-inch equals 2 divided by 0.074 equals 27 psi per 100 feet of 1.5-inch hose. So it doesn't matter if you use 13.5 or its reciprocal divided, which is 0.074, you come out with the same answer, which is 27 psi per 100 square feet of 1.5-inch hose. So to determine the friction loss in a 400-foot length of 3.5-inch hose supplying a pump with 500 gallons per minute, because the flow is greater than 100 gallons per minute, equation 12.1 applies. Just to remind you of that equation, you have friction loss equals 2Q squared plus Q. So when you plug in the numbers, you have friction loss equals 2 times 5 squared plus 5. And friction loss then, once you work out the math, equals 2 times 25 plus 5. And friction loss then equals 50.5. So friction loss works out to 55 psi per 100 feet of 2.5-inch hose. Just as a footnote, friction loss for 400 feet of hose equals 4 times 55 psi, and friction loss for 400 feet of hose equals 220 psi. To convert this figure to friction loss in 3.5-inch hose, locate the appropriate conversion factors in table 12.1. For 3.5-inch hose, we have the option of multiplying the above figure by 0.172 or dividing it by 5.80, which is the reciprocal of 0.172. So you have friction loss at 3.5-inch equals 220 times 0.172, which equals 38 psi for 400 feet of 3.5-inch hose, or Friction loss of 3.5 inch equals 220 divided by 580, which is the reciprocal of 0.172, which gives you the same number, 38 psi, for 400 feet of 3.5 inch hose. Many fire scenes require the use of multiple hose lines that often vary in lengths and sizes. When multiple hose lines supply different nozzles or apparatus, you need to calculate the friction loss for each individual hose line and set pump discharge pressures for hose that require the most pressure. Hoses needing less pressure have individual pump discharges partially closed until they are discharging the appropriate amount of pressure. Firefighting operations may require laying 2 or more parallel hose lines to supply adequate amounts of water to another pumper or a master stream device. If the hose lines were all of equal diameter, one can assume 1/2 the flow was going through each hose if there were 2 lines, or 1/3 the flow if there were 3 lines. Then use equation 12.1 to determine the friction loss for flow through that one line. Another option would be to calculate the total friction loss through both or all 3 lines using the method described above for hose that's a size other than 2.5 inch. Determine the total friction loss in the hose lay when the dual 2.5 inch hose lines, each 150 feet long, are laid to support a portable master stream device equipped with 1/2 inch tip discharging water at 80 psi. So your formula is Q equals 29.7, which is your coefficient, times diameter squared times the square root of the nozzle pressure. Then Q, once you plug in the numbers, is 29.7 times 1.5 squared times the square root of 80. And when you work out the math, you get 29.7 times 2.25 times 8.94, which gives you a flow rate of 598 gallons per minute. Assume that each hose line is carrying 1/2 the total flow. Thus, the total flow in one of the 2.5 hose lines would be Q1 line equals Q divided by 2. Q1 line equals 598 divided by 2. So Q1 line equals 299 gallons per minute. It's pretty straightforward. If it's carrying half the flow, then it's going to just be simply divided by 2 and give you the going rate, which is half of the gallons per minute that you would anticipate otherwise. Using the flow through one line, calculate the friction loss in each hose line using the equation 12.1. So here's our equation. Friction loss equals 2Q squared plus Q. So friction loss equals 2 times 2.99 squared plus 2.99. Work out the math and you get friction loss equals 2 times 8.94 plus 2.99, and therefore friction loss equals 17.9 times 2.99, and the friction loss equals 20.89 or 21 psi per 100 square feet of 2.5 inch hose. So the friction loss for 150 feet of hose equals 150 divided by 100, which gives you 21 psi. Friction loss for 150 feet equals 1.5 times 21 psi, which gives you the same number. So friction loss of 150 feet equals 31.5 or 32 psi lost in the Siamesed hose lay. Now let's look at example 12.9 from the book. Determine the total friction loss in the hose lay when the 2 3-inch hose lines and one 2.5-inch hose line, each 550 feet long, are laid to supply an attack pumper with 800 gallons per minute. Using equation 12.1, determine what the friction loss would be if the above flow were pumped through a single 2.5-inch hose line of the same length. So you have your same formula, friction loss equals 2q squared plus 2 plus q. So friction loss equals 2 times 800 divided by 100 squared plus 800 divided by 100. So you just plug in your numbers. Friction loss equals then, once you work out the math, 2 times 8 squared plus 8. And if you further extrapolate, you get friction loss equals 2 times 64 plus 8, which is friction loss equaling 128 plus 8. And friction loss equals 136 psi per 100 feet of 2.5-inch hose. Next, multiply the equivalent 2.5-inch hose figure by the actual distance of the hose length. So if you have friction loss of 550 feet, you get friction loss divided by 100 times 136 psi. Friction loss then at 550 feet equals 5.5 times 136 psi, and friction loss of 150 feet or 550 feet equals 748 psi loss in a 550 foot length of 2.5-inch hose flowing at 800 gallons per minute. Last, to convert this figure to friction loss in the 3 parallel hose lines, locate the appropriate conversion factors in table 12.1 in your book. For 2 3-inch hose lines and 1 2.5-inch hose lines, we have the option of multiplying the above figure by 0.067 or dividing it by 15, which is the reciprocal of 0.067. So you have friction loss for Siamese lines equals 748 times 0.067, which equals 50.1 or 50 psi, or friction loss for Siamese lines equals 748 divided by 15, which equals 49.9 or 50 psi. So either way you want to do it, it works out to the exact same number. What are the 2 reasons it is not advised to use underwriters' formulas to determine friction loss? See page 279 of the manual for the answers. Learning Objective 2, demonstrate how to calculate friction loss using the modern friction loss formula. Modern formula simplifies friction loss calculation by taking into account the size of the hose and the length of the lay in the original calculation. The formula is accurate over the entire range of possible flows, eliminating the need to use different formulas for different flows. Using equation 12.3 from your book, you have friction loss equals CQ squared L, given that friction loss, or FL, equals friction loss in PSI. C is the friction loss coefficient from table 12.2, which is on page 290 of your text. Q is the flow rate in hundreds of gallons per minute, or flow. And L is the hose length in hundreds of feet, length times 100. This is your table 12.2 of friction loss coefficients. It would pay to get this memorized. Most people do over time, so that on seeing you know automatically what the coefficients are. This is the remainder of the coefficient table. Any coefficient for an actual piece of hose varies with the condition of the hose and the manufacturer. So bear that in mind. Just because, for example, a 4-inch hose has coefficients of 0.374, don't count on that absolutely, because you can have conditions in the hose that can cause variance, etc. Tests confirm hose in use today has less friction loss than what is calculated with the current friction loss formula. And the reason for that is these formulas are based on a little bit older technology, and we've made advances in fire hose technology since then. When calculating friction loss in a single hose line, step 1, obtain friction loss coefficient for hose being used from table 12.2. Step 2, determine the number of hundreds of gallons of water per minute flowing, which is Q, through the hose by using the equation Q equals gallons per minute divided by 100. Step 3 is determine the quality or the number of hundreds of feet of hose, L, which is length, by using the equation L, which is feet, divided by 100. Step 4 is substitute numbers from steps 1, 2, and 3 in the equation 12.2 to determine total friction loss.
So here's one example. Determine the friction loss in a 200-foot pre-connected 1 3/4 inch attack line that is flowing 150 gallons per minute. So here's our formula. Friction loss equals CQ squared times L. So we plug in the numbers. FL equals 15.5, that's our coefficient, times 150 divided by 100 squared, times 200 divided by 100. So when we plug in or do out the math, we have friction loss equals 15.5 times 1.5 squared times 2, which calculates to 15.5 times 2.25 times 2, and that gives you a friction loss of 69.75, which you round up to 70 psi.
So let's look at the determining the friction loss in a 1,000-foot lay of 5-inch supply hose that is flowing 500 gallons per minute. The friction loss equals CQ squared L, which is our standard formula. So friction loss equals 0.08, which is our coefficient, and 500 divided by 100 squared times 1,000 divided by 100 squared. When you work out the math, that gives you friction loss of 0.08 times 5 squared times 10. And when you work out the math, that gives you 0.08 times 25 times 10. So your friction loss is 20 psi. One thing to remember is that Q equals gallons per minute divided by 100, and length equals length of hose divided by 100, which is why you see length of hose divided by 100 in this formula. That trick makes it a lot easier to manage on the fire ground. So let's look at a 2.5-inch attack line that is 150 feet long and has a reducer at its discharge end to which 100 feet of 1.5-inch hose is attached. This is from figure 12.2 in your book. The nozzle is flowing at 95 gallons per minute. Determine the total friction loss in the hose lay. Note, the pressure loss created by the reducer is not considered in this example. This will be added later in the chapter. So calculating the friction loss in a single hose line, you have a pumper with 150 feet hose at 2.5 inches, and you have a reducer that reduces the hose to 100 feet of 1.5 inch hose. That ultimately produces a nozzle pressure of 95 gallons per minute.
So let's look at calculating friction loss in a single hose line for two different hose line sizes. On the left, we've got friction loss for a 2.5-inch hose equals, there's our standard formula, CQ squared L. So friction loss for our 2.5 inch hose, when we plug in the math from our previous example, is 2 times 95 divided by 100 squared times 100 divided by 100. And when we work out the math, we have friction loss equals 2 times 0.95 squared times 1.5. That gives us, on the next line, 2 times 0.9025 times 1.5. And when you round up the math and multiply it, you get our friction loss for 2.5 inch hose is 2.7, which is 3 psi. On the right, we have friction loss for 1.5 inch hose, and there's our formula, CQ squared L. So friction loss on our 1.5 inch hose, when you plug in the math, or plug in the numbers, is 24 times 95 divided by 100 squared times 100 divided by 100. So the next line on our 1.5 inch hose gives us 24 times 0.95 squared times 1. And when you work out the math, you have 24 times 0.9025 times 1. That gives us a friction loss on the 1.5 inch hose of 21.7, which you round up to 22 psi. So our total friction loss, if you look at the bottom left, is the friction loss for total is the friction loss for the 2.5 inch hose plus the friction loss for the 1.5 inch hose. So we have 3 plus 22. So that gives us a total friction loss of 25 psi.
So let's discuss calculating friction loss in Siamesed hose lines of equal length. To increase flow rate through a given hose, additional pressure is needed to overcome friction in the hose. When conditions require great volumes of water or hose lays are long, friction loss may become so excessive that pump hose cannot supply volume of water within their design limitations. In the absence of hose with larger diameter, firefighters may keep friction loss within reasonable limits by laying 2 or more parallel hose lines to supply a needed quantity of water. So calculating friction loss in Siamesed hose lines of equal length, fire personnel have 3 options at the discharge end of these parallel lines. They can connect the lines into a multiple inlet master string device, a Siamesed appliance that in turn discharges a single hose line, or intakes of 1 or more fire apparatus with equipped pumps. Continuing with calculating friction loss in Siamesed hose lines of equal length, the same formula for single hose lines can be used for parallel or Siamesed hose lines. When calculating friction loss in Siamesed lines, use a different set of coefficients found in Table 12.3.
This is Table 12.3, which is a table of friction loss coefficients. And eventually you'll get a lot of these memorized, but you see down the left the number of hoses and their diameter in inches, and the coefficient for each down the right-hand side. So the steps for determining friction loss in a Siamesed hose would be, for step 1, you compute the total number of hundreds of gallons per minute flowing by using the equation Q, which is gallons per minute flowing, divided by 100. In step 2, if applicable, determine the friction loss in the attack line using the equation 12.3, which is the formula you're familiar with by now, which is FL equals CQ squared L, and use table 12.1 for the coefficient in this step. Step 3 for determining friction loss in a Siamesed hose line is to determine the amount of friction loss in the Siamesed lines using equation 12.3, which is FL equals CQ squared L, and use table 12.3 to obtain the coefficient in this step. And then step 4, if applicable, add the friction loss from the Siamesed lines, attack line, and 10 psi for the Siamesed appliance flow if the flow is greater than 350 gallons per minute to determine the total friction loss. The advantage of laying parallel hose lines to reduce friction loss is apparent in comparisons of test results, or if you look at the coefficients in tables 12.1 and 12.2. Tests show that when two hose lines of equal lengths are Siamesed to supply a fire stream, the friction loss is approximately 25% of that in a single hose line at the same flow and nozzle pressure. When three hose lines of equal length are Siamesed, the friction loss is approximately 10% of that in a single line at the same flow and nozzle pressure. So here's an example. A pumper attached to a fire hydrant is supplying 600 gallons per minute through 400 feet of dual 3-inch hoses equipped with 2.5-inch couplings to a pumper at the fire scene. What is the friction loss in the hose lay? Here's our formula, our old friend, FL equals CQ squared L. So let's plug in the math. The friction loss equals 0.2, that's our coefficient, times 600 divided by 100 squared, times 400 divided by 100. And then when we calculate that out, we get, on the next line, friction loss equals 0.2 times 6 squared times 4. We calculate that out, we get 0.2 times 36 times 4. So our friction loss is 28.8, which rounds up to 29 psi.
A pumper is supplying a portable master stream device equipped with a 1 3/8 solid stream nozzle discharging at 80 psi. A single 100-foot length of 3-inch hose with a 3-inch coupling is supplying the master stream device. This hose is in turn being supplied by Siamesed lines consisting of one 3-inch hose with 3-inch couplings and one 2.5-inch hose, each 300 feet long. See figure 12.3, page 296. What is the friction loss in the hose lay? Calculating the friction loss in the Siamesed hose lines of equal length, you have two 300-foot 3-inch hose couplings with, or 3-inch hoses with 3-inch couplings. And then you have a Y that splits it off into one section of 100 feet of 3-inch hose with a 3-inch coupling. So that ultimately gives you 1 3/8 pressure at 80 psi in the portable master stream device. Using example 1214 for U.S. customary, you have gallons per minute equals 29.7, which is your coefficient, D squared, which is your diameter squared, and the square inch of the nozzle pressure. The gallons per minute, once you extrapolate, is 29.7 times 1.375 squared divided by the square root of 80. And when you work out the math, you get the gallons per minute of 29.7 times 1.89 times 894, and that gives you a gallons per minute of 502. Note, because the quantity exceeds 350 gallons per minute, the appliance friction loss from the Siamesed device and the master stream nozzle will need to be factored in later. Here's an example of calculating friction loss in Siamesed hose lines of equal length. You take the friction loss at 3-inch equals CQL, which is your coefficient times your flow rate times your length, and you take friction loss at 3-inch and you plug in the numbers, equals 0.667, which is your constant, 502 feet of hose divided by 100 squared, and 100 feet of hose divided by 100. So you take your math and work it out. You have friction loss of 3-inch equals 0.667 times 5.02 squared times 1, and friction loss 3-inch equals 0.667 times 5.2 times 1, and that gives you a friction loss of 3-inch equaling 17.1, or if you round it down, 17 psi. When calculating friction loss in Siamese hose lines of equal length, using example 12.4, you have friction loss of 3 inch equals CQ squared times L. The friction loss is 3 inch equals 0.677, which is your constant. 502 feet of hose divided by 100 squared, and 100 feet of hose divided by 100. So it gives you a friction loss once you work out the math of 0.66677 times 5.02 squared times 1. And friction loss of 3 inch equals 0.667 times 25.2 times 1. And then when you finish working out the math, you get 17.1 or 17 psi. Now if you look at the right side, you have friction loss of Siamese lines equals CQ squared L. The friction loss of Siamese lines equals 0.27, which is your coefficient, times 502 divided by 100 squared, times 300 divided by 100. So you have friction loss of Siamese lines equals 0.27 times 5.02 squared times 3. And when you work out the math, it gives you friction loss of Siamese lines equals 0.27 times 25.2 times 3. And the friction loss of the Siamese lines works out to 20.4 or 20 psi. Now, if you look at the bottom, you have friction loss total plus friction loss of 3 inch plus friction loss of Siamese lines plus the Siamese device plus the master stream nozzle. That gives you a friction loss total of 17 psi plus 20 psi plus 10 psi plus 25 psi. And that gives you an overall total of friction loss of 72 psi.
When determining your own friction loss coefficients, the actual coefficient that should be applied to a specific hose varies with a number of factors, including the age of hose, the manufacturer of hose, the design of hose, how well the hose has been maintained, and the number of bends, cracks, and creases in the hose.
Departments that wish to know exact coefficients of hose can request specific friction coefficient for a particular hose from a manufacturer when it is purchased. They can also test their own hose to determine actual coefficients, and there's a procedure for determining friction loss and calculating coefficient for a particular hose, and that is simple if equipment is available. Before performing these tests, several basic principles must be considered. Use the same hose in the test that will be used on the fireground. Conduct tests on hose that is in service. Test only one type of hose at a time. Test results are only as accurate as the equipment used to obtain them. Equipment needed to conduct these tests. You need a pitot tube or flow meter, 2 inline gauges, preferably calibrated in increments of 5 psi or less, hose to be tested, a smoothbore nozzle if using a pitot tube, any type of nozzle if using a flow meter, and worksheet 12.1. You can see across the column you have test run 1, pump discharge pressure psi, pressure gauge 1 psi, etc. Flow from flow meter by equation. So all of these things are constructive and vital to a proper test, and so this worksheet will be used every single time. And here is the conclusion of the worksheet. It must be used every single time. If you're determining friction loss in any size hose, step 1 is to lay out on a level surface lengths of hose to be tested. Lay out 300 feet if the hose is in lengths of 50 feet, 400 feet if the hose is in lengths of 100 feet. Step 2 is to connect one end of the hose line to a discharge on a pumper being used to carry out the test. Connect a nozzle to the opposite end of the hose line. If using a pitot tube, use a smooth bore nozzle. If using a flow meter, any nozzle is suitable.
Step 3, insert gauge 1 in at the hose line at the connection between the first and second sections of hose away from the discharge. Make this connection 50 feet from the pumper if the hose being tested is in 50-foot lengths, or 100 feet from the pumper if it is in 100-foot lengths.
Step 4. Insert gauge 2 at a distance of 200 feet from gauge 1, regardless of the length of the hose sections. You should have 50 feet of hose between gauge 2 and the nozzle if using 50-foot hose lengths, or 100 feet of hose between gauge 2 and the nozzle if using 100-foot lengths. Using a flow meter, do not insert anywhere between the gauges. Okay, here you see determining friction loss in any size hose. You see 50 to 100 feet from the pumper, 200 feet between the flow meters, and another 50 to 100 feet in between the engine ultimately and the pitot. Determining friction loss in any size hose. Again, step 5. When all appliances have been inserted into the hose line, begin the tests. Supply water to a hose line at a constant pump discharge pressure for the duration of each test run. Make 3 or 4 test runs for each size hose. You may use different pump discharge pressures for different runs as long as they remain constant within the same test run. Use sufficient pump discharge pressure to produce a satisfactory fire stream from the nozzle. Step 6. Once water is flowing, record pump discharge pressure, readings from gauge 1 and gauge 2, and from the flow meter or pitot gauge in the appropriate spaces of worksheet 1. That's the worksheet that I showed you a moment ago. Step 7. Complete worksheet 12.1 as instructed on the table to get the friction loss coefficient for particular hose. Determining your own friction loss coefficients. Actual testing, calculation of specific coefficients will give a more accurate picture of friction loss characteristics in the hose at that point in time. As hose ages and is used repeatedly for emergency operations, its internal condition will deteriorate and cause more friction loss, thus changing the coefficient. In most cases, the coefficient will become larger due to increased friction loss in the hose. To know accurate hose-specific friction loss coefficients for a particular hose over its lifetime, test it periodically and adjust the coefficient. Review questions. How did the modern formula for calculating friction simplify the process? See page 314 of your text. When 2 hose lines of equal lengths are Siamesed to supply a fire stream, how does friction loss compare to that of a single hose line at the same flow and nozzle pressure? That will be on page 322 of your text. Learning Objective 3. Demonstrate how to determine elevation pressure between a fire pump and a nozzle. Another cause of pressure loss or gain in a hose lay is a change in the elevation between the pump and the nozzle. Fireground operations often require the use of hose lines at varying elevations. The effects of elevation on pressure in hose lay must be considered when determining total pressure loss. When a nozzle is operating at an elevation higher than the apparatus, this pressure is exerted back against the pump. you can see how the water flows downhill and puts pressure on the pump. This pressure is exerted back against the pump, and to compensate, you need to add elevation pressure to the friction loss to help determine total pressure loss. Operating a nozzle lower than the pump results in pressure pushing against the nozzle. The subtracting elevation pressure from total friction loss compensates for this, and the pump has to do less work to supply proper discharge pressure to the nozzle. As you can see the water flowing downhill, the pumper's compensating by pumping less water because of gravity flow, adding to the fire stream for the firefighters. When determining elevation pressure, this is from equation 12.4. You have to use the elevation pressure equals 0.5 H. Given that EP is elevation pressure, loss or gain in PSI, 0.5 is a constant, that's your coefficient, and H is height in feet. So if you use equation 12.5, US customary, EP equals H divided by 2, given that EP is elevation pressure, loss or gain in PSI, 2 is a constant, and H is height in feet. And we're going to see how this works in just a moment. Using either of these equations will provide a workable figure for elevation pressure, loss or gain. To estimate pressure loss or gain in a multi-story building, many fire professionals prefer to use the equation based on the number of floors rather than feet. And that is equation 12.6. And the formula reads EP equals 5 psi times the number of stories minus 1. So it's elevation pressure equals 5 psi times the number of stories minus 1. An example 12.15. Calculate the total elevation pressure loss for a hose line operating at the top of an 80-foot hill. This is in figure 12.7 in your book. The elevation pressure is 0.5 H. The elevation pressure is 0.5 times 80 because it's 80 feet high. So the elevation pressure equals 40 psi. Or the elevation pressure equals H divided by 2, height divided by 2. And the elevation pressure is 80 divided by 2 because the height is 80 feet. So the elevation pressure is 40 psi. Here's an example of determining elevation pressure. You see the pumper at the bottom, and it's overcoming 80 feet of height so that it can provide adequate pressure to the firefighters at the top of the ridge. A hose line connected to a building standpipe system is operated on a fire on the 13th floor. What is the total pressure loss due to elevation at the base of the standpipe system? We have elevated pressure equals 5 psi, which is your coefficient, times the number of stories minus 1. So if you extrapolate the work, you get elevation pressure equals 5 psi, 13 minus 1 times 13 minus 1. So elevation pressure equals 5 times 12. So elevation pressure is 60 psi. Review question. How do you determine total pressure loss when a nozzle is operating at an elevation higher than the apparatus? See page 314 of your manual for the answer. What happens to pressure when operating a nozzle at a lower elevation than the pump? That will be on page 322 of for your answer. Learning objective 4. Demonstrate how various types of hose layouts affect total pressure loss. With hose layout applications, rarely are hose lays as simple as those calculated in the previous section. An almost endless configuration of fire hose may be used during the course of an emergency scene operation. Various appliances used in fireground hose also cause pressure loss. To make connections necessary for the situation, fireground operations often require use of Hoseline appliance, including increasers, gates, Siamesed standpipe system, reducers, Ys, manifolds, and aerial apparatus. Here's an example of a reducer, and here's an example of a Y unit. Here also is an example of a manifold, and on the right you see an example of an aerial apparatus. With appliance pressure loss, as water flows from a hose into and through these devices, a certain amount of pressure or friction loss occurs. The amount of friction loss varies with each type of appliance. The appliance friction loss generally is considered significant only in cases where total flow through the appliance is at least 350 gallons per minute. Assume no pressure loss for flows less than 350 gallons and a 10 psi loss for each appliance other than a master stream device in a hose assembly when flowing 350 gallons or more. These include Ys, gated or not, Siamesed, reducers and increasers, hose manifolds, and including LDH manifolds. The FDC to sprinkler and standpipe systems if pressure loss in the system piping is calculated separately. The hose discharges in standpipe systems if pressure loss in system piping is calculated separately. Friction loss caused by handline nozzles is generally insignificant in the overall hose assembly. Assume a friction loss of 25 psi for all flows through the following systems or devices: master stream appliances, fixed aerial apparatus waterway systems, and standpipe systems. The only sure way to determine the exact friction loss of each appliance is to conduct friction loss tests. There are simple hose layouts that include single hose lines, equal length multiple hose lines, equal length wide hose lines, and equal length Siamesed hose lines. Single hose lines are most commonly used hose lay and require the simplest friction loss calculations. From example 12.7 in your text, a customer is supplying a 300-foot hose line with 125 gallons per minute flowing. A hose line is composed of 200 feet of 2.5-inch hose reduced to 100 feet of 1 3/4-inch hose. This is in figure 12.9. What is the pressure loss due to friction in the hose assembly? Well, you have friction loss of 2.5 equals CQ squared L. So it's a variation on the regular formula that we use. So friction, if we keep working, friction loss 2.5 equals 2 times 125 divided by 100 squared times 200 divided by 100. And remember that your hose line is always divided by 100. Next line, you have friction loss 2.5 equals 2 times 1.25 squared times 2, because you're just working out the math. You've plugged in the numbers. And the next line is friction loss 2.5 equals 2 times 1.5625 squared. And friction loss 2.5 totals 6.25 or 6 psi. Here's an example of a single hose line. You have a pumper with 200 feet of 2.5-inch hose with a reducer that reduces it to 100 feet of 100 or 1.3/4-inch hose, and that produces a stream of 125 gallons per minute. Here's another example. This is 12.17. Change the formula to friction loss 1 3/4. So friction loss 1 3/4 equals CQ squared L. So it's the same formula again. You just change the friction loss to 1 3/4. So if you keep working the math, you have friction loss 1.3/4 equals 15.5, which is your coefficient, times 1.25 squared times 1. And then you keep working, and friction loss 1.5 equals 15.5 times 1.5625 times 1. So friction loss 1 3/4 equals 24.22 or 24 psi. The friction loss total equals friction loss 2.5 plus friction loss 1 3/4 plus the appliance loss if it's greater than 350 GPM. The friction loss total equals 6 psi plus 24 psi plus 0 psi, so your flow is less than 350 gallons per minute. So your friction loss total is 30 psi.
Here's example 12.18. A fire is discovered on the 8th floor of a structure. An arriving engine company proceeds to the 7th floor of the structure and connects 150 feet of 2.5-inch hose to the standpipe outlet, and then proceeds to the 8th floor to attack the fire. The hose line is equipped with 1 1/8-inch tip solid stream nozzle that will be flowed at 50 psi. Determine the total pressure loss due to friction and elevation pressure at the standpipe system fire department connection. Use rule of thumb for friction loss in the standpipe system. So using that example, let's figure this out. On the top left, we have Q, which is our flow rate, times 29.7, which is our coefficient, times diameter of the hose squared, times the square root of the nozzle pressure. And then when we plug in the math, we get 29.7 times 1.125 squared times the square root of 50. And calculate that out, you get 29.7 times 1.12656 times 7.07. And that calculates out to a flow rate of 266 gallons per minute. If you look to the right of that, our EP, or elevation pressure, is 5 psi per number of stories minus 1, so that's easy. We take elevation pressure, in this case, is 5 psi times 8 minus 1, which is 5 times 7, so our elevation pressure is 35 psi. At the bottom left, here's our friction loss in the 2.5-inch line equals CQ squared L. So our friction loss equals 2, which is our coefficient, times 266 divided by 100 squared, which take the math from our previous example, times 150 divided by 100. You work out the math, you get 2 times 2.66 squared times 1.5. That gives you friction loss in your 2.5-inch hose of 2 times 7.08 times 1.5. And that calculates out to friction loss in the 2.5-inch line is 21.2 or 21 psi. So our friction loss total in the bottom right is friction loss of the 2.5-inch hose line plus elevation pressure plus standpipe system loss. So we have 21 psi on our 2.5-inch hose line plus 35 psi, which is the elevation pressure, plus 25 psi, which is the pressure loss at the standpipe connection. So our friction loss total is 81 psi. So in this example, our pumper is got a line of 300 feet of 4-inch hose. Our elevation is 20 feet, and you can see that we're losing pressure due to the elevation. So that gives us a total output of 500 gallons per minute on our portable master stream device. This is just an illustration of that.
For friction loss 2, you go to example 12.19. So it's a slight variation on the regular formula, which is friction loss 4 equals CQ2L. The friction loss 4 equals 0.02, which is your coefficient, 500 divided by 100, which is your hose length, divided by 100 squared, and 300 divided by 100, which is your hose length divided by 100. Then you continue the math. Friction load 4 equals 0.02 times 5 squared times 3. The friction load 4 equals 0.2 times 25 times 3. So your friction load 4 equals 15 psi. Then you have the height consideration over on the right. You have your elevation pressure equals 0.05 psi H. And then the next line is elevation pressure is 0.05 psi times 20 feet. So it gives you an elevation pressure of 10 psi. So you work those out together and you have friction loss total equals friction loss 4 plus EP, which is elevation pressure plus appliance loss. The next line is friction line total equals 15 psi plus 10 psi plus 25 psi. That gives you a friction loss total of 50 psi. You have multiple hose lines of equal length. When determining friction loss in equal length, multiple lines whose diameters are the same only perform calculations for one line. When diameters of hose lines vary, you calculate the friction loss for each hose line and set pump discharge pressure for the highest pressure. The corresponding valve on any hose requiring less pressure is partially closed to reduce the pressure from that discharge. Here's an example. A pumper is supplying two pre-connected hand lines being used to fight a garage fire. The attack line is 200 feet of 2-inch hose equipped with a 200 gallon per minute fog nozzle. The exposure protection line is a 200-foot 1-inch booster line flowing at 35 gallons per minute. You can find this in figure 12.11, page 310 in your book. What is the total pressure loss due to friction in each hose line, and upon which line should the operator base the pump pressure? Let's work this out. Here's your multiple hose lines of equal length. You got your pumper with 200 feet of 2-inch hose, two sections of it, and you've got 200 feet with a 1-inch booster hose, and then you've got 200 feet of 2-inch hose working on the main fire. So multiple hose lines equal length. You got your standard formula, FL2 equals CQ2L. So friction loss 2 equals 8, which is your coefficient from your table. 200 minus 100 squared, because you got 200 feet of line divided by 100, times 200 divided by 100. So you take again your 200 yards of line divided by 100. So you have friction loss squared equals 8 times 2 squared times 2. Continue to work out the math. You have friction loss 2 equals 8 times 4 times 2. So your friction loss 2 is 64 psi. Now for the second line, you have FO1 equals CQ2L. they should work out the same. You have friction loss 1 equals 150 times 35 divided by 100 squared times 200 divided by 100. So friction loss 1 equals 150 times 0.35 squared times 2. Friction loss 1 equals 150 times 0.1225 times 2. So the friction loss 1 equals 36.75 or 38 psi. The answer is the pump pressure must be based on the 2-inch attack line and the booster line valve must be gated down. So you've got two lines of equal length, but they're running different pressure. So the pump pressure must be based on the 2-inch attack line and the booster line valve must be gated down. Fire departments may have pumping apparatus to set up to quickly develop wide hose lines for multiple head fire attack. This involves the use of one supply line wide into 2 or more smaller attack lines. The attack lines may range in size from 1.5 to 2.5 inches, and wide lines should be the same length diameter to avoid having two different nozzle pressures and a difficult friction loss problem. When nozzle pressure, hose length, and diameter are the same on both lines, Y appliances equally splits total water flowing. This requires pumps operator to consider only one length of wide hose lines when computing total pressure loss. When you have wide hose lines of equal length and diameter, and these are used to fight fires at occupancies such as garden apartments, one line is often placed at a higher elevation than the other. The pressure loss should be calculated on the worst case basis, which means elevation pressure of the line on the upper floor should be factored in. It is unlikely that elevation difference between these two lines would be so great that the lower lines would be dangerously overpressurized. If the difference is significant, partially close the valve on the Y to the line, requiring less pressure. Compute the number of hundreds of gallons per minute flowing in each wide line. Step 1. Compute the number of hundreds of gallons per minute flowing in each wide hose line. And step 2. Determine the friction loss in one of the wide attack lines using equation 12.3. Step 3. Compute total number of hundreds of gallons per minute flowing through the supply line to the Y by using the following equation. Q total equals gallons per minute in attack line to the first power plus gallons per minute in attack line to the second power divided by 100. Step 4 is to determine friction loss in the supply line using the Q total as the figure for Q in equation 12.3. Step 5, to determine total pressure loss, add friction loss from the supply line, one of the attack lines, and 10 psi for Y appliances if the total flow exceeds 350 gallons per minute, and calculate elevation pressure if applicable. Here's an example. Determine the pressure loss due to friction in a hose assembly in which 2 and 1 3/4 inch hose lines, each 150 feet long and flowing 125 gallons per minute, are wide off 300 feet of 2.5 inch hose. This comes from figure 12.12 on page 312 in your text. Here we see calculating friction loss in an equal length wide hose assembly. You have your pumper with 300 feet of 2.5-inch hose. You have your Y, and then off of the Y you have two lines each of 150 feet of 1 3/4 hose, delivering 125 gallons per minute each. When calculating friction loss in an equal length wide hose assembly, you have a couple things to consider. First, let's take each line. First, friction loss in 1 3/4 equals CQ squared L. So it's again a variation on our regular formula. So you take friction loss 1 1/2 equals 15.5, which is our coefficient from our table. 125 divided by 100 squared, because that's our hose line, divided by 100 squared. 150 divided by 100, so it's our hose line divided by 100, times friction loss at 1 3/4 inches. So you take the numbers and you continue to calculate. Friction loss at 1 1/4 equals 15.5 times 1.25 squared times 1.5. That equals friction loss of 1 3/4 equals 15.5 times 1.625 times 1.5, and you come up with the calculation of friction loss of 1 3/4 at 36.33 or 36 psi. Now, when you take the other line, because they're equal length wide hose line assembly, you take friction loss at 2 1/2 times CQ total squared L. So the formula is slightly different. You take the numbers and plug them in. So you have friction loss 2 1/2 equals 2, which are coefficient, times 125 plus 125 divided by 100. Those are our hose lengths divided by 100 squared. And 300 divided by 100, that's a hose length divided by 100. So you take your friction loss at 2 1/2 equals 2 times 250 divided by 100 squared times 3. You continue the math and you end up with friction loss at 2 1/2 equals 2 times 2.5 times 2 times 3. And that comes out to friction loss 2 1/2 equals 2 times 6.25 times 3. And the total is friction loss 2 1/2 equals 37.5 or 38 psi. And you can see that they're actually very similar. Friction loss total equals friction loss at 2 1/2 plus friction loss at 1 3/4 plus appliance loss if greater than 350 gallons per minute. And that comes out to friction loss total at 36 psi plus 38 psi plus 0 psi. So your flow is less than 350 gallons per minute. So your ultimate total is friction loss total at 74 psi. Let's look at another example. This is 12.22. Determine the pressure loss due to friction in a hose assembly in which two 2.5-inch hose lines, each 200 feet long and equipped with a 1 1/4 inch tip solid stream nozzle to be operated at 50 psi, are wide off 500 feet of 4-inch hose. One of the nozzles will be operated off the roof of a building that is 30 feet above street level. So let's use our formulas. First, we have Q equals 29.7 times the diameter squared times the square root of nozzle pressure. So that is gallons flowing times or equals the coefficient times the diameter squared times the square root of the nozzle pressure. So let's plug in the numbers. Q equals 29.7 times 1.25 squared times the square root of 50. We work out the math. Q equals 29.7 times 1.5625 times 7.07. That gives us a flowing rate of 328 gallons per minute. Now let's look at friction loss. Friction loss at 2.5 equals CQ squared L. So friction loss 2.5 equals 2 times 328 divided by 100, which is our hose length, divided by 100 squared, times 200 divided by 100, which is our hose length, divided by 100. And then we look at friction loss 2.5 equals 2 times 3.28 squared times 2. And friction loss at 2.5 equals 2 times 10.76 times 2. We're just working out the math. So it gives a friction loss at 2.5 of 43 psi. Example 12.22. Let's look at elevation pressure. Elevation pressure is 0.5 psi foot per head. And so the next step is to take elevation pressure at 0.5 psi per foot times 30 feet, because that is our elevation. And so it's very simple calculation. Our elevation pressure is 15 psi. If we look to the right, we see friction loss at 4 times C times Q total squared times L. Friction loss 4 equals 2 times 328 plus 328 divided by 100. So that's our hose lines divided by 100 squared times 500 divided by 100. That's hose length divided by 100. So friction loss 4 equals 0.2 times 656 divided by 100, because you're just doing the math, squared times 5. So the next step is friction loss 4 equals 0.2, which is our coefficient, times 6.56 times 2 times 5. And when we work out the math, we get friction loss 4 equals 0.2 times 43 times 5, and friction loss 4 equals 43 psi. So if friction loss total equals friction loss at 2.5 plus EP plus friction loss 4 plus appliance loss if greater than 350 gallons per minute, the friction loss total equals 43 psi plus 15 psi plus 43 psi plus 10 psi, means there's a flow of greater than 350 gallons per minute. So our friction loss total is 111 psi. It's just a simple matter of plugging in the numbers once you know the formulas. With Siamese lines, a pumper is supplying an aerial ladder equipped with a detachable ladder type and a 500 gallon per minute fog nozzle. The pumper is supplying 2 Siamesed 3-inch hoses with 2.5-inch couplings. Each hose is 300 feet long. These lines are Siamesed into a single 100-foot section of 3.5-inch hose that is attached to the ladder pipe. The tip of the ladder is elevated approximately 60 feet. This will be in figure 12.3, page 314. Determine the total pressure loss of this arrangement. So here's your diagram. You've got first pumper with each hose, it's 300 feet at 3 inches with 2.5-inch couplings. Here's your Siamese connection. And then that's feeding 100 feet of 3.5-inch hose. And this is going up the quint, the ladder elevated at 60 feet and pumping at 750 gallons per minute. So let's work out the math. You have friction loss at 3.5 equals CQ squared L. So let's plug in the numbers. Your friction loss 3.5 equals 0.34 times 500 divided by 100 squared, which is your hose length, divided by 100 squared, times 100 divided by 100, which is your hose length, divided by 100. The next line, you have friction loss of 3.5 equals 0.34, which is your coefficient from the table, 5 squared times 1. Then you have friction loss of 3.5 equals 0.34 times 25 times 1. And you work out the math, and your friction loss at 3.5 is 8.5 or 9 psi. Now for Siamese lines, you have friction loss at Siamese lines equals CQ squared L. The friction loss at Siamese lines equals 0.2 times 500 divided by 100 squared, that's your hose length, divided by 100 squared, times 300 divided by 100. So you work out the math. Your friction loss at Siamese lines equals 0.2 times 5 squared times 3. The friction loss for Siamese lines equals 0.2 times 5 times 3. And when you finish calculating out the math, you get a friction loss at Siamese lines of 15 psi. This is example 12.23. You have elevated pressure of 0.5 psi foot per head. Your elevation pressure is 0.5 psi feet times 60 feet. So it's a very simple calculation. Your elevation pressure is 30 psi. Now, if you have a friction loss total equaling a friction loss of 3.5 plus friction loss from Siamese lines plus EP plus appliance loss if it's greater than 350 gallons per minute, you have friction loss total that equals 9 psi plus 15 psi plus 30 psi plus 10 psi, which is Siamese, plus 25 psi, which is the ladder pipe. So you add these together and you get a friction loss total of 89 psi. It's pretty straightforward. Fire personnel may confront fireground situations that require hose lines of varying sizes and lengths. Calculate each line individually and determine which part of the layout has the greatest amount of pressure loss. Set the pump discharge for the line that has the highest friction loss and gate down so other lines, pump panel, or gated Y or manifold so they will not be overpressurized. Multiple hose lines of unequal length can result from the addition of a new hose line to a pumper, the addition of hose lengths to an existing line, the pulling of multiple pre-connected attack lines that differ in diameter and length. When unequal length and diameter hose lines are used, the amount of friction loss varies in each line, and the pump operator must calculate the friction loss in each hose line. Let's look at example 2.24. A pumper is supplying 4 pre-connected attack lines at a structure fire. 2 of the lines are 200 feet of 1 3/4 hose equipped with 3 1/4 inch tip solid stream nozzle operating at 50 psi. The third line is 150 feet of a 1.5 inch hose line equipped with a 125 gallon fog nozzle. The fourth line is a 250 foot 3 inch attack line equipped with a 1 1/4 inch tip solid stream nozzle operating at 50 psi. Determine the total pressure loss due to friction in each hose line and upon which line to base the pump discharge pressure. So this one's going to be a little more complicated. You got lines 1 and 2 and line 3. So lines 1 and 2, you've got gallons per minute, which is 29.7, which is your coefficient, your diameter squared times the square root of the nozzle pressure. That's the standard formula. So your gallons per minute equals 29.7, and you plug in the numbers, 0.75 squared times the square root of 50, and you calculate it out. Gallons per minute is 29.7 times 0.5625 times 7.07. So you're running at a rate of 118 gallons per minute. Line 2, you have friction loss of 1 3/4, which is CQ squared L. That's your standard formula. So you plug in your numbers. Friction loss of 1 3/4 equals 15.5. That's your coefficient, times 118 divided by 100. That's your hose line divided by 100 squared. And 200 divided by 100. That's your hose line divided by 100. And you take your friction loss of 1 3/4 equals 15.5 times 1.18 squared times 2, and then you continue the math, which is friction loss 1 3/4 equals 15.5 times 1.39 times 2, and that is friction loss 1 3/4 of 43.2, or if you round it up, 43 psi. Now line 3 is friction loss at 1/2. That gives you friction loss 1/2 at CQ2L. Same formula, but you're dealing with a different friction loss. Next line, you plug in the numbers. Friction loss 1 1/2 equals 24 times 125 over 100, which is your hose line divided by 100 squared. And 50 divided by 100, which is hose line divided by 100. And then you take 15 friction loss of 1 1/2 equals 24 times 1.25 squared times 1.5. And that gives you friction loss of 1/2 equals 24 times 1.5625 times 1.5. You're just working out the math. And that gives you a total of friction loss in 1/2 of 56.3 or 56 psi. So lines 1 and 2, you're running 118 gallons per minute. The line with 1 3/4 nozzle, you're running 43 psi friction loss, and line 3 with 1 1/2 coupling, you're running 56 psi friction loss. For line 4, you're running gallons per minute of 29.7 times diameter squared times the square root of nozzle pressure. Again, your standard formula. So let's plug in the numbers. Gallons per minute equals 29.7 times 1.25 squared times the square root of 50. So your gallons per minute is 29.7 times 1.5625 times 7.07. That gives you a gallons per minute of 328 gallons per minute. Now your friction loss 3 equals CQ2 squared, CQ squared L. That's your standard formula. So you plug in your numbers. Friction loss 3 equals 2 times 328 divided by 100 squared. That's your hose line divided by 100 squared. And 250 divided by 100. That's your hose line divided by 100. So you take your friction loss and plug in the numbers, which is 2, and that's your coefficient from your table, times 3.28 squared times 2.5, and you work out the math. Friction loss 3 equals 2 times 10.76 times 2.5, and that gives you a friction loss of 53.8 or 54 psi. The total pressure loss in the system is based on the line with the highest loss, which in this case would be line 3 at 56 psi. So let's look at multiple hose lines of unequal length. A pumper supplying 2 hand lines that are being used to protect exposures and 1 large diameter hose that is supplying an aerial master stream. 1 hand line is a 250-foot length of 2.5-inch hose supplying 175 gallons per minute fog nozzle at ground level. The second hand line is a 200-foot length of 1.5-inch hose supplying a 95 gallon per minute fog nozzle positioned on the roof of a 28-foot high exposed garage. The aerial device is equipped with a piped waterway that has a 1,000 gallons per minute fog nozzle and is raised 80 feet. It is being supplied by 300 feet of 5-inch hose. Determine the total pressure loss due to friction in each hose line and upon which line to base the pump discharge pressure. So let's take a look at that. We've got a 2-inch hand line with a friction loss of 2 equals CQ2L. That's our standard formula. So we plug in the numbers. Friction loss 2 equals 8, which is our coefficient from the table. 175 divided by 100, which is our hose length, divided by 100 squared, times 250 divided by 100, which is our hose length, divided by 100. So if we continue to work out the math, we have friction loss 2 equals 8 times 1.75 squared times 2.5. And the friction loss 2 equals 8 times 3.06 times 2.5. And we ultimately come to the answer of friction loss 2 equals 61.3, or if we round it, it's 61 psi. Now let's look at the 1.5-inch hand line. With friction loss 1.5 equals CQ2L. That's our standard formula. So we have friction loss 1.5 equals 24, which is our coefficient from the table, times 95 divided by 100, which is our hose line, divided by 100 squared, times 200 divided by 100, which is our hose line, divided by 100. So we take friction loss 1.5 equals 24 times 0.95 squared times 2, and our friction loss 1.5, if we continue to work out the math, equals 24 times 0.9025 times 2, and it gives us a friction loss of 43.3, or if we round it, 43 psi. If we look to the right, we have elevation pressure. Elevation pressure is 0.5 psi foot per head, and the elevation pressure in the next line is 0.5 psi feet times 28 feet, and that gives us an elevation pressure of 14 psi. Now let's look at the bottom. Friction loss total equals friction loss 12 plus elevation pressure. So we have friction loss total, which is 43, plus 14, which is our elevation pressure. So our friction loss total is 57 psi. Now we're going to look at a 5-inch supply to an aerial device. The FLS 5 equals CQ2L. That's our standard formula. And in this case, we're looking at friction loss with a 5-inch supply to an aerial device. So let's look at the math. Friction loss 5 equals 0.08, and that's the coefficient from our table, times 1,000 divided by 100, that's our hose line, divided by 100 squared, times 300 divided by 100, that's hose line, divided by 100. So we take our friction loss 5 and work out the math. 0.08 times 10 squared times 3, and friction loss 5 equals 0.08 times 100 times 3, which gives us a friction loss 5 of 24 psi. Now if we look at the elevation pressure, we have 0.5 psi feet per head, And that gives us an elevation pressure of 0.5 psi feet per head, which is 80 feet. And that gives us a total of elevation pressure of 40 psi. The friction loss total equals the friction loss 5 plus the elevation pressure plus the appliance loss if the flow exceeds 350 gallons per minute. So that gives us a friction loss total of 24 plus 40 plus 25. So our friction loss total comes to 89 psi. Our total pressure loss in the system is based on the line with the highest loss, which in this case would be the line supplying the aerial device at 89 psi. Let's look at wide hose of unequal length, diameter, and/or elevation. When wide lines are of unequal length or diameter and/or operated at different elevations, there are unequal water flows at the split and the Y appliance. Determine the friction for each unequal length wide lines and then use the line with the greater pressure loss in the final calculation for the entire hose lay. Some Ys have a 2.5 inch intake and two 2.5 inch discharges. A single 2.5 inch supply may be used to supply two separate 2.5 inch attack lines of this type of Y. It is more hydraulically efficient to use 3 or 3.5 inch hose equipped with 2.5 inch couplings or with a reducer to supply this type of Y. Now, a wide hose line of unequal length, diameter, and/or elevation is also known as a water thief. This is used to divide supply hose into more than two attack lines. It's equipped with a 2.5 inch intake, and on the discharge side, it is equipped with one 2.5 inch discharge and two 1.5 inch discharges. Now let's talk about manifold hose lines. The introduction of large diameter supply hose has led to a variety of other manifolds designed to divide water from a single LDH supply line. Manifolds have one LDH intake and as many as 5 discharge connections. Typically, the smallest discharge connection on this type of manifold would be 2.5 inches. A manifold may also have more than one LDH discharge connection. Hose lines requiring less than the maximum pressure are gated down at the Y or the manifold. Gating down lines at a manifold to achieve proper pressure in each line is a guessing game unless the Y or manifold is equipped with a pressure gauge on each discharge. To calculate friction loss in an unequal length wide or manifold hose line, for step 1, you must compute the number of hundreds of gallons per minute flowing in each wide hose line by using Q, which is discharge in gallons per minute, divided by 100. Step 2 is to determine friction loss in each wide line using equation 12.3. Step 3 is to compute total number of hundreds of gallons flowing in the supply line to the Y or the manifold by adding the sum of the flows in the attack lines and then dividing by 100. Step 4 is to determine friction loss in the supply line using equation 12.3 minus the friction loss equals C times Q total squared times L. Step 5, add friction loss from the supply line, Y, or manifold appliance, and if the total flow is greater than 350 gallons per minute, elevation loss, and wide line with the greatest amount of friction loss to determine total pressure loss. So let's talk about calculating friction loss in unequal length wide or manifold hose lines. Here's an example. Determine the total pressure loss due to friction and elevation pressure for a hose line assembly in which one 300-foot 3-inch hose with a 2.5-inch coupling is supplying two attack lines. The first attack line consists of 200 feet of 1 3/4-inch hose stretched through the front door of a structure. It is flowing at 150 gallons per minute. The second attack line is 250 feet of 2-inch hose that is carried up a ground ladder and stretched through a second floor window. It is flowing at 200 gallons per minute. So let's look at the attack line 1. Here's our formula. Friction loss at 1 3/4, because that's the size of the hose, equals CQ2 squared L. Equals CQ squared L. So it's the same formula. We're just figuring out friction loss for 1 3/4. So if we move to the next step, it's friction loss at 1 3/4 equals 15.5, which is our coefficient, times 150 divided by 100, which is the length of our hose, divided by 100 squared, times 200 divided by 100, which is the length of the other hose, divided by 100. So we have friction loss at 1 3/4 equals 15.5 times 1.5 squared times 2. We're just plugging in the numbers. The next line is friction loss at 1 3/4 equals 15.5 times 2.25 times 2. So the ultimate answer is friction loss at 1 3/4 equals 69.75, or if you round it up, 70 pounds per square inch of friction loss on the 1 3/4-inch attack line. If we look at attack line 2, we get friction loss for 2 equals CQ squared L. So friction loss 2 is 8, which is our coefficient from our table. 200 divided by 100, which is the hose length, divided by 100 squared, times 250 divided by 100, which is the hose length, divided by 100. And the next line, we plug in the numbers. Friction loss 2 equals 8 times 2 squared times 2.5. And if you work out the math, you get friction loss 2 equals 8 times 4 times 2.5. So our answer is friction loss on line 2 is 80 psi. If you look to the right, you have to consider elevated position because your second line is elevated up through the second window. So you have elevation pressure of 5 psi plus or times the number of floors minus 1. So that's the easy calculation. So your elevation pressure is 5 psi, and you've got 2 stories minus 1, so 2 minus 1. So your elevation pressure is 5 psi times 1, so your elevation pressure is 5 psi. So at the bottom, we put them together. We put the friction loss 2 plus total plus the elevation pressure. So we have friction loss 2 total equals friction loss squared plus the elevation pressure. So the friction loss 2 total equals 80 plus 5. So friction loss for 2 total is 85 psi. And that is for the attack line 2 plus its elevation pressure. Now let's look at the supply line with a 3-inch with a 2-inch coupling. You have friction loss for supply line 3 equals CQ total squared times length. Friction loss 3 equals, let's plug in the numbers, is 0.8 times 150 plus 200 divided by 100. So it's your hose length added together divided by 100 squared times 300 divided by 100, which is your other hose length divided by 100. So you have friction loss 3 equals 0.8, which is your coefficient. 350 divided by 100 squared times 3. And you just work out the math. Friction loss on 3 is 0.8 times 3.5 squared times 3. So the next line is friction loss for 3 is 0.8 times 12.25 times 3. And once you've extrapolated all the math, you get friction loss on 3 as 29.4 or 29 psi. And this is again calculating friction loss in unequal length, wide, or manifold hose lines. Here's an example. Total pressure loss. The total pressure loss in the system is based on the attack line with the higher loss, which in this case would be line 2, plus the friction loss in the supply line. Because the flow rate is 350 gallons per minute, adding in the appliance loss is also required. So your formula reads as friction loss total equals friction loss on 2 plus friction loss on 3 plus the appliance loss. So your next line is friction loss total equals 85 plus 29 plus 10. So friction loss total is 124 psi. Now let's look at example 12.27, and again these are all in your book. Determine the total pressure loss due to a friction for a hose line assembly in which one 500-foot 3-inch hose with 3-inch couplings is supplying 3 attack lines attached to a water thief. The first attack line consists of 150 feet of 1.5-inch hose flowing at 125 gallons per minute. The second attack line is 100 feet of 1.5-inch hose flowing at 95 gallons per minute. The third attack line is 150 feet of 2.5-inch hose flowing at 225 gallons per minute. Take a look at figure 12.4, page 320 for reference. This is actually that same diagram. So you've got your pumper with 500 feet of 3-inch hose with 3-inch couplings. Then you have your water thief, which is dividing up those lines. So you have a line that's 100 feet of 1.5-inch hose. That's one attack line. Then you have 150 feet of 2.5-inch hose, and then 150 feet of 1.5-inch hose. And you can see how, since they're unequal length, wide or manifold hose lines, they have different discharge pressures. One has 95 gallons per minute, one is 225 gallons per minute, and one is 125 gallons per minute. Now let's look at calculating friction loss in unequal length, wide or manifold hose lines. First, let's look at example 12.27 from your book. Attack line 1, which is 1.5 inches. So you have friction loss 1.5 equals CQ squared L. If you notice, no matter what the size of the attack line, the formula CQ squared L is always the same. So advancing to the second line, we have friction loss 1.5 equals 24, which is our coefficient from our table, times 125 divided by 100, which is our hose length divided by 100 squared, times 150 divided by 100, which is hose length divided by 100. And then we have friction loss at 1.5 equals, once we plug in the numbers, 24 times 1.25 squared times 1.5, and when we extrapolate the math, we get friction loss at 1.5 equals 24 times 1.5625 times 1.5, and our friction loss at 1.5 equals 56.3, which when we round is 56 psi. That's attack line 1 at 1.5 inch. Now let's look at attack line 2 at 1.5 inch. We have friction loss 1.5 equals CQ squared L. Again, the same formula. Friction loss at 1.5 equals 24, which is our coefficient. And because we're running a slightly different hose length, our numbers are going to be slightly different. So we have friction loss on the second line here. We have friction loss at 1.5 equals 24 times 95 divided by 100. That's our hose length divided by 100 squared times 100 divided by 100, which is our hose length divided by 100. And then in the third line, we have friction loss at 1.5 equals 24 times 0.95 squared times 1. And our next line, we have friction loss at 1.5 equals 24 times 0.9025 times 1. So our friction loss for our second attack line is friction loss at 1.5 equals 21.7 or 22 psi. So you can see how, even though they're both 1.5 inch lines, because they're different lengths, they're going to have different friction loss levels. Now let's talk about calculating friction loss in unequal length wide or manifold hose lines, looking at attack line 3 and supply line 3 with 3-inch couplings. So let's look at attack line 3 with a 2.5 inch coupling. So we have friction loss at 2.5 equals CQ squared L, again same formula. So friction loss 2.5 equals 2 times 225 divided by 100 squared, which is your hose length divided by 100 squared, times 150 divided by 100, which is hose length divided by 100. And our friction loss at 2.5 equals 2 times 2.25 squared times 1.5. We're just plugging in the numbers. And then let's work out the math. The next line is friction loss at 2.5 equals 2 times 5.0625 times 1.5. And our friction loss at 2.5 equals 15.2 or 15 psi of loss. That's for attack line 3 with 2.5 inch coupling. Now let's look at the supply line, which is a 3-inch, with a 3-inch coupling. So we have friction loss equals C, which is our coefficient, times Q total, because it's a supply line, so it's our total gallons flowing squared times length. So our next line is friction loss equals 0.677. That's our coefficient from the table. And our next line, our next entry is 125 plus 95 plus 225 over 100. Those are the different hose lengths, and they're divided by 100 squared, times 500 divided by 100, which is hose length divided by 100. The next line is friction loss equals our coefficient, 0.677, times 4.45 squared times 5. So we just work out the math. The next line is friction loss equals 0.677 times 19.8025 times 5. That gives us a friction loss of 67 psi. So that's for the supply line and running at 3 inches with 3-inch couplings. So let's look at example 12.27. This is total pressure loss. The total pressure loss in the system is based on the attack line with the highest loss, which in this case would be line 1, plus the friction loss in the supply line. Because the total flow rate exceeds 350 gallons per minute, it's necessary to add the 10 psi appliance loss. So our formula is friction loss total equals friction loss for line 1 plus friction loss for 3 plus appliance loss. So our next line reads friction loss total equals 56 plus 67 plus 10. We just added in the numbers. So our friction loss total is 133 psi. Here's an example, 12.28 from your book. Determine the total pressure loss due to friction for a hose line assembly in which one 600-foot 5-inch hose is supplying 3 hose lines attached to large diameter hose manifold. One hose line is 200 feet of 4-inch hose supplying a portable master stream device. The master stream is discharging 80 psi through a 1/2 inch tip. The second hose line is 150 feet of 2.5 inch hose equipped with a 250 gallon per minute fog nozzle. The third hose line is 250 feet of 3-inch hose with a 2.5 inch couplings flowing at 275 gallons per minute through a fog nozzle. So let's break this down. We have our master stream, which is gallons per minute, equals 29.7. That's our coefficient from our table, times the diameter squared times the square root of nozzle pressure. So if we follow the next line, gallons per minute is 29.7 times 1.5. That's the size of our nozzle squared times the square root of 80, which is our nozzle pressure, the square root of our nozzle pressure. So the math works out 2 gallons per minute at 598 gallons per minute. The next line is friction loss for 4 equals CQ squared L. Again, the same formula. So friction loss for 4 is 0.2 from our coefficient table. 598 divided by 100, which is length of hose, divided by 100 squared, times 200 divided by 100, which is the second hose length, divided by 100. So friction loss 4, once we plug in the numbers, is 0.2, which is our coefficient, times 5.98 squared times 2. And the next line, friction loss 4 equals 0.2 times 35.6704 times 2. And friction loss 4 equals 14.3 or 14 psi. The friction loss total is this next thing we have to look at. Friction loss total is friction loss 4 plus the appliance loss. So the friction loss total is 14 plus 25. So friction loss total is 39 psi. Continuing with calculating friction loss in unequal length wide or manifold hose lines, let's look at example 12.28. We've got one 2.5 inch hand line. So let's take a look at the friction loss for that. Friction loss for the 2.5 is C times Q squared times L, against the same formula. Friction loss for 2.5 is 2, which is our coefficient, times 250 over 100, which is our hose length, divided by 100 squared, times 150 over 100, which is our second hose line. So friction at 2.5 is 2 times 2.5 squared times 1.5. So friction loss for 2.5 is 2 times 6.25 times 1.5. So friction loss for 2.5 is 18.75 or 19 psi. Now let's look at a 3.5 inch hand line with a 2.5 inch coupling. We have friction loss for 3, the 3-inch hand line, which is C Q squared L, same formula. So we plug in the numbers. Friction loss 3 is 0.8, that's our coefficient, times 275 divided by 100 squared, which is our hose length, divided by 100 squared, times 250 over 110, which is our other hose line, divided by 100 squared. So friction loss 3, once we plug in the numbers, is 0.8 times 2.75 squared times 2.5. So friction loss 3 is 0.8 times 7.5625 times 2.5. So friction loss 3 for 3-inch coupling or 3-inch hand line is 15.1 or 15 psi. Let's look at a supply line from a 5-inch. We have friction loss equals C times Q total squared times length. And the reason we're looking at Q total is because the 5-inch is a hard line and it's going to be supplying maximum flow. So our next line is friction loss equals 0.8, which is our coefficient, times 598 plus 250 plus 375 divided by 100, which is our hose lengths, divided by 100 squared, times 600 divided by 100, which is our other hose length, divided by 100. So our next line is friction loss equals 0.08 times 11.23 squared times 6. We're just working out the math. So the friction loss is 0.08 times 126.1129 times 6. So our friction loss is 60.53 or 61 psi. Now let's look at total pressure loss again. The total pressure loss in the system is based on the attack line with the highest loss, which in this case is the 4-inch line supplying the master stream, plus the friction loss in the supply line. Because the total flow rate exceeds 350 gallons per minute, it is necessary to add the 10 psi appliance loss. So we have friction loss total equals friction loss 4 plus friction loss 5 plus the appliance loss. So that means that we have friction loss total equals 39 plus 61 plus 10. So our friction loss total is 110 psi. The primary difference between calculating friction loss for a master stream hose arrangement and hand lines is the greater volume of water that master streams flow. To supply necessary volume of water to the master stream device, the nozzle often will be fed by 2 or 3 medium diameter 2.5-inch or 3-inch hose lines, MDH, or 1 LDH. Most master stream nozzles used by municipal fire departments are capable of flows up to 1,000 gallons per minute. These can be safely supplied using 3 MDH hoses or a single LDH supply line. Some aerial devices may have nozzles that can flow as much as 2,000 gallons per minute. Achieving that flow may require 2 or more LDH supply hoses. Some industrial fire brigades may have very large master stream nozzles capable of flows up to 15,000 gallons or more. Nozzle discharging more than 15,000 gallons of water may need to be supplied from 6 to 8 5-inch supply hoses or larger supply hoses being pumped from 2 or more large capacity industrial pumpers. Concepts using in determining friction loss for master streams are essentially the same as what is used for other fire streams. The only difference occurs if hose lines of unequal length or diameter are used to supply master stream appliances. In regards to master streams, if hose lines supplying master stream devices are of unequal lengths but the same diameter and are being pumped from the same pumper, determine the average of the hose lengths. Add the length of each hose line and divide the sum by the number of hose lines being used. When possible, use coefficients for wide hose lines in Table 12.3, which you see on slide 54, and of course it's in your text. If Table 12.3 does not give a coefficient for the hoses in use, average the length of the lines and assume an equal amount of water is going through each hose. If multiple hoses are different lengths and diameters, are supplying a single master stream, they cannot be combined into a single hydraulic calculation. Each hose must be calculated separately. Pump discharge pressure will be based on the line requiring the highest amount of pressure. Manual aerial devices with piped waterways are treated the same as master stream appliances. Use a friction loss of 25 psi to include pressure losses. Elevation pressure loss is calculated separately. For exact figures, consult aerial manufacturer for specific friction loss data or perform field tests to derive data. If traditional detachable ladder pipe and hose assembly are used, friction loss within Siamesed, hose, and ladder pipe must all be accounted for. Here's an example. This is 12.29 from your text. A 5,000 gallon per minute master stream device is being set up to attack a petroleum storage tank fire. 2 industrial pumpers will supply the master stream nozzle, and we will assume that each is supplying 1/2 of the required volume. Pumper 1 is pumping through 2 6-inch hoselines that are each 700 feet long. Pumper 2 is supplying 3 5-inch hoselines that are each 500 feet long. This is demonstrated in figure 12.16. Determine the total pressure loss in each hose assembly. Here's your illustration. You got one pumper, each hose at 700 feet of 3-inch hose, and your other pumper, which each hose of 500 feet at 5-inch diameter. So let's look at pumper 1. We know that each pumper will be responsible for supplying 2,500 gallons per minute. Since pumper 1 is supplying 2 hose lines, we will assume that each 6-inch line is carrying 1,200 gallons per minute, or 1,250 gallons per minute. Thus, friction loss for 6 equals CQ squared L, which is the same formula, CQ squared L, as always. So friction loss for 6 is 0.05, which is our coefficient, times 1,250 divided by 100. That's our total fire hose line divided by 100 squared, times 700 divided by 100, which is the other hose line divided by 100. So we take friction loss 6 equals 0.05 times 12.5 squared times 7. So friction loss 6 equals 0.05 times 156.25 times 7. So we're just working out the math. So friction loss for 6 is 56.7, which when you round it up is 57 psi. Now let's talk about pumper 2. Since pumper 2 is supplying 3 hose lines, we will assume that each 5-inch line is carrying 833 gallons per minute. Thus, FL5 equals CQ squared L, same formula again. So friction loss for 5 equals 0.08 times 833 divided by 100 squared, which is our hose line, divided by 100 squared, times 500 divided by 100, which is our other hose line, divided by 100. So we take friction loss for 5 equals, we're just adding the numbers, 0.08 times 8.833 squared times 5. So friction loss for 5 is 0.08 times 69.39 times 5. So friction loss for 5 is 27.75 or 28 psi. Now let's look at another example. This is 12.30. A pumper is supplying an aerial device equipped with a piped waterway. The aerial device is elevated 70 feet and is discharging 900 gallons per minute. One 3.5-inch hose line is 450 feet long and the other is 500 feet long. Assume that each line is supplying half the volume. Determine the total pressure loss in this hose assembly. Since the table 12.3 does not list a coefficient for dual 3.5-inch hose lines, calculate the friction loss using the flow through each line and the average of the two lengths of hose. So here's the math. We have friction loss for the 3.5-inch line equals CQ squared L, which is our typical formula. So if friction loss for 3.5-inch line equals 0.34, which is our coefficient, times 450 over 100, which is our hose line divided by 100 squared. And then we have times 450 plus 500 squared over 100. That's our second hose line. And then on our third line, we have friction loss at 3.5 equals 0.34 times 4.5 squared times 475 over 100. So we're just working out the math. Next line, friction loss at 3.5 equals 0.34 times 4.5 squared times 4.75. So the next line, we continue the math. Friction loss at 3.5 equals 0.34 times 20.25 times 4.75. So our total is friction loss for 3.5 is 32.7 or 33 psi. Now our elevation pressure is 0.5 psi feet per head. So our elevation pressure is 0.5 times 70, so 70 feet. So when you take 70 and divide it by 2, you get elevation pressure of 35 psi. So in example 12.30, we have total pressure loss. We have friction loss total plus friction loss at 3.5-inch coupling plus elevated pressure plus appliance loss. So our friction loss total is 33 plus 35 plus 25. So our friction loss total overall is 93 psi. Some review questions. How should you calculate friction loss for fireground operations that use multiple hose lines with varying diameters? Please see page 314 of your book for the answer. The next question is, what is the primary difference between calculating friction loss for master stream hoses and hand lines? Please see page 322 of your text. For learning objective 5, we're going to state the different methods for determining fireground hydraulic calculations. If calculations must be performed on the fireground, the driver operator can rely on the following methods for determining pressure loss and required pump discharge pressure: flow meters, hydraulic calculators, pump charts, the hand method, condensed Q formula, and gallons per minute flowing. Flow meters measure the volume of water in gallons per minute. The volume of water flowing through the hose assembly is not reduced, and whatever amount of water is pumped into a hose must be discharged at the other end. Flow meters reduce the number of pressure calculations required of the driver operator. They make it possible for the driver operators to pump correct volume of water to the nozzles without having to know the length of hose line, amount of friction loss, or elevation of nozzles. If both the nozzle and pump discharge are open, the driver operator needs only to increase the engine throttle until the flow meter shows that 125 gallons per minute is flowing through the line. Flow meters are particularly advantageous when supplying hose lines or master stream devices equipped with automatic nozzles. Automatic nozzles may lead the driver operators to supply insufficient discharge pressures, but flow meters make it easier to ensure adequate flow rate. NFPA Standard 1901 allows the use of flow meters only instead of pressure gauges on all discharges 1.5 to 3 inches in diameter. It provides discharges with 3.5 inches or larger that may be equipped with flow meters, but must also have accompanying pressure gauges. A flow meter must provide a readout in increments no larger than 10 gallons per minute. For flow meter applications, regardless of which type of flow meter is used on a fire apparatus, properly calibrated flow meters can reduce the difficulty of certain conditions faced by driver-operator in a number of situations. Let's talk about diagnosing water flow problems. A flow meter can be used as a diagnostic tool to identify water flow problems. If flow does not increase when the driver-operator increases pressure, several problems are likely. Either the hose is kinked, a midline valve may be partially closed, or a vehicle tire is parked on the hose line. Continuing with diagnosing water flow problems, if firefighters on a line advise a pump operator or IC of a loss of water at a nozzle, but a flow meter shows no reduction or perhaps even an increase in flow, personnel can assume the hose has burst and will need to be replaced. Now let's discuss relay pumping. Use of flow meter during relay pumping makes it possible to feed supply line without having to know the number of gallons flowing from the pumper receiving the water. This is done by monitoring the master discharge gauge and the flow meter as the throttle is increased during the setup stage of the operation. As the engine speed or RPM increases, so do discharge and gallons per minute reading from the flow meter. With relay pumping, increasing engine speed until the flow meter reading no longer increases sets the pump at the correct discharge pressure to supply adequate flow to the receiving pumper. Pump operators should watch the master intake pressure gauge and not allow incoming pressure to drop much below 20 psi. Now let's discuss standpipe operations. To supply necessary volume, pressure of water into the system, firefighters need to relay some basic information: the number of hose lines to be supplied, and the rated or desired volume to be flowed by each nozzle. This information allows pump operators to add all flows from the nozzles and the pump that volume water into the system. As long as the flow meter shows that flow, the pump operator is supplying the system with adequate volume and pressure. With standpipe operations, once the hose line or hose lines is or are charged, there is no flow through the system until the nozzle or nozzles is or are opened. The pump should be set for discharge pressure relatively close to what will be required when the nozzles are flowing. Once the nozzle or nozzles is or are fully opened and flowing, the driver operator can adjust discharge pressure until the appropriate amount of water is flowing. During standpipe operations, the pump operator must be in communication with firefighters on the nozzles to ensure nozzle pressures and reactions are correct. Now let's mention hydraulic calculators. These can be used to determine friction loss and pump discharge pressure required to supply a hose layout. This eliminates the need to do calculations mentally or on paper. There are three basic types: manual, mechanical, and electronic. Let's talk about manual and mechanical calculators. These have a slide or dial that indicates water flow, size of hose, and length of hose lay. By moving the slide or dial to line up each of these components properly, the driver operator can then read the amount of friction loss or required pump discharge pressure. With electronic hydraulic calculators, these allow the driver operator to input known information such as water flow, size of hose, length of hose lay, and any elevation changes. They may be portable or mounted near the pump panel, and apps and other programs may be installed on electronic phones and tablet devices. Pump charts reduce the need for calculations on the emergency scenes. These are known as cheat sheets. They contain required pump discharge pressures for various hose lays and assemblies the department uses. They may be placed on laminated sheets carried on the apparatus or on plates affixed to the pump panel itself. Departments may develop their own pump charts or use those supplied by fire hose or nozzle manufacturers. Pump charts supplied by manufacturers may typically contain a lot of information that will not apply to the particular jurisdiction. To develop and use the pump chart, it is important to understand column headings. The nozzle headings should include only those nozzles and devices used by the department. The nozzle column indicates nozzle pressure being produced. Columns headed 100, 200, and so on indicate the number of feet of hose being used to supply a given nozzle layout. The chart should include other applications such as sprinkler system support and relay pumping operations. The first step in developing a pump chart is to identify all nozzles, devices, and layouts used by the department and then enter them in a nozzle column. Then enter rated or desired flow in gallons per minute and desired nozzle pressure for each item in appropriate columns. If the master stream device may be supplied by either 2.5 inch or 3 inch hose, make separate entry for each layout in the nozzle column. The second step is to calculate required pump discharge pressures for each listed layout. Observe the following rules when making these calculations. Include pressure loss in master stream appliances, aerial devices, and hose appliances when flowing in excess of 350 gallons per minute. For wide hose lines, the length of the layout numbers indicates the number of feet of hose between the pumper and the Y. If the attack lines are kept pre-connected to the Y, they should be calculated into the overall figure. When a master stream nozzle may be supplied by a different number or size of hose lines, indicate these on the chart. Round the pump discharge pressure answers onto the chart to the nearest 5 psi. Do not list the pump discharge pressures that exceed the test pressure used for the size of hose concerned. When calculating pump discharge pressure for relay operations, provide established department residual pressures at the intake of the pumper being supplied. To use a pump chart, locate the nozzle column and nozzle layout being used on the chart. Follow that line across to the vertical column headed by the number of feet of hose in that layout. Figure in the block where two columns intersect, and that's required pump discharge pressure. Let's look at an example. Using table 12.4, determine the pump discharge pressure for a master stream device that is equipped with a 1 3/4 inch solid stream nozzle tip and is supplied by two 2.5 inch hose lines, each 200 feet long. Here's your pump chart in length of lay feet. So you got your nozzles listed down the left, all different kinds between boosters, pre-connect, wide lines, and master streams. And then across the top, you have gallons per minute, nozzle pressure, and then length of lay in feet. This is the remainder of that same chart, table 12.4, and it's in your book. Locate the master string device with 1 3/4 inch nozzle tip in the left column of the chart. Choose the one that follows the device being supplied by two 2.5 inch lines. Follow this line to the column for a 200-foot hose length. You should land on the figure 169 psi. This is the required pump discharge pressure. So go back, use that chart, follow it correctly, and you should come up to 169 psi. Now let's talk about hand or counting fingers method. Driver operators use the hand or counting fingers method for determining friction loss in 2.5 inch hose. It's not as complicated as it sounds, but here goes. Starting with the thumb of the left hand, each finger is numbered at the base in terms of hundreds of gallons per minute. Returning to the thumb and again moving from left to right, the tip of each finger is given a successive even number beginning with 2. The numbers 3, 5, 7, and 9 can be used for flows of 150, 250, 350, and 450 gallons per minute respectively. These are half hundred figures that can be assigned to the spaces between the fingers. So if you move along the base of the fingers, those are whole numbers of gallons per minute. The fingertips are single digits, successive even numbers beginning with 2 on your thumb, and then the numbers 3, 5, 7, and 9 can be used for flows of 150, 250, 350, half 100 figures, and those can be assigned between the fingers. This is an illustration of that. So you see at the base of each finger, you see a whole number, starting with the thumb, 100 gallons per minute, first finger, 200 gallons per minute, third finger, 300 gallons per minute, ring finger, 400 gallons per minute, pinky, 500 gallons per minute. Then you see successive numbers, single numbers across the top. Starting with the thumb, you have 2. You have a space between the thumb and first finger, which is 3. First finger 4, between that 5, middle finger 6, etc. And then you see half flow gallons, 150, 250, 350, 450 between the fingers. So for the hand or counting fingers method, the friction loss for 100 feet of 2.5 inch hose at the desired flow, you select the appropriate finger and multiply the number at the tip of the finger by the first digit at the base of the finger. The friction loss for a flow of 500 gallons per minute, you use the numbers assigned to the little finger, or 5 times 10 equals 50 psi friction loss per 100 feet of 2.5 inch hose. If you use friction loss for a flow of 200 gallons per minute, use the numbers assigned to the index finger, or 2 times 4 equals 8 psi friction loss under 100 feet of 2.5 inch hose. It's a lot simpler than it sounds, and if you practice it, you get it in a snap. Note, this method, which has no metric conversion, gives a reasonable estimate of the expected friction loss in any particular hose line. If a more accurate figure is required, one of the other methods must be employed. So these are field ground hydraulics. It's not the same as calculated hydraulics. So with the hand or counting fingers method, using the hand method, determine the total pressure loss due to the friction in 200 feet of 2.5 inch hose when a fog nozzle is flowing at 200 gallons per minute at 100 psi. Well, you take 2 times 4, and that gives you 8 psi loss per 100 feet. 8 times 200 divided by 100 is 16 psi loss in the hose assembly. All you have to do is apply these numbers to the hand, and you'll easily see this. Here's another example. Using the hand method, calculate the total pressure loss due to friction in a 2.5 inch hose line, 300 feet long, with 350 gallons flowing through the line. You take 3.5 times 7, that gives you 24.5 psi loss divided by 100 feet. So if you take 24.5 times 3, that gives you 73.5 psi loss in the hose assembly overall. Here's another example. Using the hand method, what is the total pressure loss due to friction in a 1 3/4 inch hose line, 200 feet long, with 175 gallons per minute flowing through the line? Remember where your numbers are assigned on your hand. You get 4 times 9 is 36 psi loss per 100 feet. So if you take 36 times 2, that gives you 72 psi loss in the hose assembly overall. Now let's talk about the condensed Q formula. The condensed Q formula with minor variations can be used to determine friction loss in 3, 4, and 5 inch hose. The condensed Q formula, or 3 inch hose, is a basic unaltered condensed Q formula and is for calculating friction loss in 3 inch hose. It does not matter whether the hose has 2.5 or 3 inch couplings. It's not as accurate as FL equals CQ squared L, but it is faster and sufficiently precise for fireground operations. Okay, let's review the condensed Q formula for 3 inch hose. The amount of friction loss calculated using a condensed Q formula will be 20% greater than if the same situation is calculated using the FL equals CQ squared L. This can mean a difference as high as 50 psi in a 1,000-foot 3 inch hose lay. With this knowledge, the pump operator may adjust calculated pump pressure accordingly. Here's an example. FL equals Q squared, given that friction loss per 100 feet FL equals friction loss per 100 feet of 3 inch hose, and Q is the number of hundreds of gallons per minute flowing. Let's look at the condensed Q formula for 3 inch hose. Here's an example. What will be the total pressure loss due to friction when 300 gallons per minute is being discharged from a nozzle attached to 200 feet of 3 inch hose? Let's look at the example on the left first. Friction loss equals Q squared. So we plug in the numbers. We have friction loss equals 300 divided by 100, because you take your amount divided by 100 squared, and friction loss equals 3 squared, so friction loss is 9 psi per 100 feet. Now if you look at the right side, you have friction loss total equals friction loss per 100 feet times length. So friction, once you plug in the numbers, you have friction loss total equals 9 times 200 divided by 100. Friction loss total equals 9 times 2, so friction loss total is 18 psi. With a simple modification, the condensed Q formula can be used to calculate friction loss in a 4 inch supply hose. So here's the example. Friction loss per 100 feet equals Q squared divided by 5, given that FL is friction loss in 100 feet of 4 inch hose. Q is number of hundreds of gallons per minute, and 5 is a constant. Okay, so let's look at this example. What will be the total pressure loss in 600 feet of 4 inch hose flowing at 800 gallons per minute? The friction loss equals Q squared over 15. We're looking at the left side. So friction loss is 800 divided by 100 squared divided by 5. So our friction loss total equals friction loss per 100 feet times length. So if we continue to do the math, we have friction loss total equals 13 times 600 divided by 100. So friction loss total is 13 times 6, and our ultimate answer is friction loss total is 78 psi. If you look at the right side, you have friction loss equals 8 squared divided by 5. So friction loss is 64 divided by 5, and friction loss is 12.8 or 13 psi per 100 feet. With another simple modification, condensed Q formula can also be used to calculate friction loss in 5-inch supply hose. So the formula is friction loss equals Q squared over 15, given that FL is friction loss in 100 feet of 5-inch hose, Q is number of hundreds of gallons per minute, and 15 is a constant. So here's your example. What will be the total? Let's look at the left side first. What will be the total pressure loss in 500 feet of 5-inch hose flowing at 1,000 gallons per minute? We use our formula, friction loss equals Q squared over 15. We plug in our numbers. Friction loss equals 1,000 divided by 100 squared over 15. So our friction loss total equals friction loss per 100 feet times length. So friction loss total is 7 times 5, and our ultimate friction loss total is 35 psi. On the right hand side, we have friction loss equals 10 squared over 15. Friction loss equals therefore 100 over 5. So our friction loss is 6.67 or 7 psi per 100 feet. Some review questions. What makes flow meters particularly useful for fireground hydraulic calculations? You need to see page 326 and 327 of your manual for an answer. Next question. What information is contained in a pump chart? That's on page 329 and 330 for your answer. Class, as always, there are a lot of technical things in several of these chapters. If you have any questions, please make sure that you see your instructor, and thank you for your time and careful attention. Always remember, this is a supplement to the study of your text. You must rely on the text as your main basis of information. But again, that being said, if you have specifics that require clarification, be sure to contact your instructor. Thank you again. We'll meet again for Chapter 13.